Hi everyone. Guess we'll get started here. Welcome to another Haskell study group. I'm your host Ram Bedam with Atlanta Functional Programming. Uh, Today we'll be continuing our discussion of the algebraic data types that are available in Haskell, what they are, how they were, how you can construct them, as well as provide some intuition as to some of the theory behind their purposes. Last time we talked and had a brief overview of data declarations, data type constructors, and introduced the notion of a kind. If you recall, a kind being essentially this uh, type on top of types, where we know whether or not a type is either a concrete type, as noted by the star, versus a type that requires an actual concrete type to be passed in order to be um, in order to be applied in a type construction to actually be created, right? And this is noted by the star arrow star. Okay. And we also talked about some issues related to how types are normally leveraged, the notion of the type construction being used in type signatures, classes, type class declarations, and instances, and so forth. We talked also briefly about the differences between nullary constructors. Today we'll be talking about unary data constructors as well, and we'll introduce later on record types that are and how to define using record syntax a data constructor for a type constructor, so that you can actually get your um, familiar dot syntax to actually go and access information related to a particular type. We'll also be going through some other interesting things that have been available in Haskell that I think we've introduced in past episodes, particularly the new type and what it represents, but we didn't actually dig into some of the nuances on what a new type actually does behind the scenes and why it's important to use new type versus just simply creating a data constructor with a single argument representing a concrete value. But that will be later on in the program in today's episode. And hopefully, given times, we'll also talk through about normal form and deconstructing values and stuff. But I would like to spend time on at least my understanding of these algebraic data types discussions, and also go through some exercises just to drive home some of the stuff that was mentioned in the book. The main sections that we'll be covering today are essentially section 11.8 through 11.12 in the book. Time permitting, we might be adding the section 11.13 on constructing and deconstructing values, and then next week we'll cover and have a discussion on what a function type being exponential is, higher kind of data types, and so forth. If we breeze through the next couple of things in this discussion on algebraic data types, then I will go ahead and dive into that material. I just feel like this is something a little bit more fundamental and requires some understanding and may require some discussion prior to actually discussing some of these other things related to higher kinds and polymorphic lists and so forth. Because this is kind of the very foundation at which a lot of data types are defined inside Haskell, and it's necessary to know what Haskell means by having support for algebraic data types. Now, that said, I'm going to give just a brief history because I actually dug into this a little bit, and at least according to Wikipedia and a couple of other places, Haskell might be the first language or one of the few languages that has supported it, but it's not actually the first language that introduced the notion of algebraic data types. It was actually another Edinburgh language that's from this lineage that Haskell adopted the ADT construct, and that's hope. I encourage you all to actually look up hope in Wikipedia and see it. It's actually a pretty neat ML derivative, and its syntax for folks coming from looking at Haskell a lot, or even Miranda, its predecessor, this will not look unfamiliar to you. It very much leverages a lot of the stuff that Haskell ended up adopting with some more modern syntax. But what we didn't cover last time, and what we're going to be talking about today, is why is it called an algebraic data type? And I think that's important to first discuss. The way the book describes it is because of the notion of having sums and products that they're, and I'm going to quote the book here, patterns of argument structures using two basic operations, sum and product, is one of the reasons why algebraic data types are in Haskell are algebraic. I didn't kind of like this definition, to be quite honest. I prefer actually what Wikipedia defined it as, which is a composite data type formed by combining other types using either product types, which, for example, records are one, struct types. We've used product types in many other programming languages. They weren't called product types at that time. They were called structs, or they were called records, and so forth, or even tuples is a product type. And some types are essentially something we've used in C, actually, the pattern or notion of the tagged union data structure. Remember, union data structures inside C essentially creates a single field of size of the largest member of the union, and you end up having to add some additional machinery to manage, well, what is actually stored in this particular location. With the tagged union pattern, that was nothing more than creating in C a enumeration of some sort, or even a integer ID, if you will, meant to implying what field you're ultimately trying to access, and it'll go ahead and have a function that will they'll take in that union and return the appropriate value based on an implicit cast. That is a type of sum type, and variance, even in C++, is kind of its successor. In Haskell, you do not need to do all of that, because with sum types in Haskell, you could simply define it using this simple logical disjunction. And we've seen an advantage of this when we looked at Boolean and integer last week. The one thing to note about both sums and products, and this also goes to the heart of this algebraic data type discussion, is they provide a way to reason about your types, specifically in the realm of cardinality, to determine the number of cases a specific type could instantiate or could create itself, okay? So this is really connected to the notion of the number of values a particular variable of a specific type can represent. So this can, if you will, allow one to recognize if specific types need to be more restricted or they need to be expanded, because you can look at the number of cases based simply on the cardinality of the type that you're dealing with, and you can determine whether or not something is out of bounds or not. All right. Now, obviously, this analogy of using a set theoretic definition and this notion of cardinality tends to break or fall apart when you start talking about the notion of using infinite data structures. However, that being said, most often what ends up happening with an infinite data structure is most people end up taking a sample of the infinite data structure. They don't just sit on the entire infinite data structure because obviously it's infinite. The program will keep on going. So it is it's impossible, or even in some cases useless, to actually go and just directly access the infinite data structure. You would end up using other accessors, at which point you are actually projecting, you're selecting a subset of the information, which means you'll almost always end up dealing with a finite set, and you can actually go and look at then the number of values that particular type can represent. I'm not, trivializing it, the fact that infinite lists can be used in many different cases. I'm just merely saying that the analogy can fit even in that kind of situation, especially when you recognize that the specific number of values that you're going to be dealing with is a representation of the subset that you're going to be handling, not necessarily the whole set. That's coming off of the infinite data structure. Algebraic data types, when talking about this reasoning portion, again, like I said, allows you to handle cases, but and this notion of handling the number of cases is very useful when you're starting to reason about runtime behavior of a specific Haskell program. Take, for instance, the Haskell data type int8. Okay, I think it's called int8. Data constructor. Let's go. Oh, 1 second. I may have. Oh shoot, that's not what I want to do. Let me just open this guy again, and info is what I want to use. Okay. Okay, hold on 1 second. Maybe I have to do import data.int. Okay, and now I could do info int8, and we'll get information about int8. Okay, so let's take, for example, int8. Okay, this is kind of the one of the things that in the book it's represented. Now, technically, int8 is not a sum type or a product type. It is pretty well defined. But there are 256 values of int8, 0 to, well, it's actually technically, since it's a signed 8-bit integer, it's minus 128 to 127. But the point is you could technically in Haskell define this, because it's small enough, as a sum type of minus 128 or minus 127 or minus 126 all the way up to 127. At which point you have the finite set of 256 values in runtime behavior that you could end up leveraging. All right. We've also looked at bool, which is our standard one, which is either false or true. Now recall that with bool, we have these two nullary constructors, false or true, that don't take any arguments. And remember, when we discussed bool, we mentioned the fact that these can also be treated as constant values. Okay, from the standard of the algebraic type definition terminology, this is also an algebraic type, specifically a sum type, but it's an algebraic type with two values. Okay. And the main reason why it's two values is obviously you have false and you have true, okay? And you each one of them represents one value that could be instantiated, okay? and especially since these do not take an integer, this becomes very, very important to recognize. We could see many other examples. We've actually written a couple of them earlier in here in our code. We could write one where we have a data constructor called bad, all right, which consists of behavior, if you will, and that's considered either bad or good. All right, this is another example of a two-value sum type that takes in nullary construction. Okay, and you can recognize again that these two values are the two cases that you need to necessarily define at the runtime. Okay. As you are going on and going through these sum types and product types definitions, you're going to start thinking about the number of values that you need to handle. And ultimately, you're going to write the appropriate pattern matches that are required in order to encompass all of those cases. Remember, specifically in, like, say, the true case, we had this situation where you needed to write, you couldn't just simply write true and then be done with any particular function, right? A function definition, because what will end up happening is you'll have a case where if it's actually not true or false, it's not going to hit anything, and you'll have a fall. If you don't have a fall through case, Haskell will complain. It will say that there's no case to actually handle this particular pattern. You can even see this when you do enum from, okay, and we start looking at false, like the cardinality of this, okay. This might be somewhat useful when you're dealing with types that are very finite, that you defined either enumerated cases like this case, like bool, or behavior, or you write your own. But when you are dealing with a type that requires another type variable, remember the number of cases of the type that's going to be generated is a function of the cardinality of the concrete type that's passed in. All right. So take, for instance, our sum type ba that we defined last time. Okay. Ba requires you to specify a type variable. Now, if you specify an int 8 here by making, say another type constructor called ba8 equals ba int 8, okay, and let's go ahead and for this example do a data.int here. I'm pretty sure that I'm doing this right. Oops, so I forgot I have to put this guy down here. Now we have this, okay? This ba8 construction here that we have, this type, basically is a type constructor that has 256 runtime values. You know this because, again, it's an 8-bit integer. There are 256 values in the set of 8-bit integers, so we have 266 runtime values. You can actually use that to reason through and ensure that you've written all the cases for the 256 values. Does this make sense for folks? It allows you to also test things as you are going through this particular as you're practicing type design and you're practicing using sum types and product types. Knowing this cardinality will help you ensure that your test suite has appropriate coverage. All right. When we start talking about tests, I will bring this up again, but keep this in mind. You can use this for reasoning as you're doing code review, but you could also use this to verify that your tests are appropriately covering everything, right? We've already seen several examples of null-array constructions, so I won't bore you with different null-array constructions just because last week we kind of beat that with with the stick. I will mention though these single constructions, these unary constructions that we introduced kind of last time and over the past few weeks. That's a completely important topic to cover in terms of what they represent and what they can support and not support. Okay. Again, when you're dealing with unary types, data constructors, the representation and the cardinality of the underlying type is going to be determined based on the concrete type that was passed into the type construction. So if you had, say, a good example of this, is the example that we had. So this is adopted from the book in chapter 11, Haskell book. This has something called, they were talking about animals and goats and farm animals, but everybody likes dogs, so I like using dogs for also for this. All right. You might have a type constructor called dogs that's equal to dogs int, and then we have obviously this deriving thing that generates the appropriate type class instances for EQ and show, so that we can display information about this. And if we go and look at this now, we do t dogs 8, we'll see that it's going to be of type dogs, and we can actually go in and leverage this in other places too. That means also that we get some type checking for free. So like if we try to do dogs A, you'll see that we'll get a complaint that we're trying to pass in a string, which is treated as a list of characters, into something that requires an integer. All right. One also important thing to note is this type construction here that takes in a generic type variable. It's going to create a new instance for every type that you define it on. All right. So it's not. Think of that type variable, that generic type variable, like creating a type template. Okay, it's going to instantiate itself only at the time that a concrete type has been passed in. This is why, if you recall, if we pass in or do kind of, we'll end up getting a function application notation with star arrow star, and that's because of the fact that star represents a concrete type, and this star arrow star means that it is a function that takes in a concrete type and returns you a concrete type and instantiates it. One interesting result that comes from this reasoning about cardinality for type constructions and stuff, especially when it comes to unary constructions, unary constructors, especially given the fact that their cardinality is determined on the underlying type, the number of values that the type that is created is based on the underlying type that's being that's used, the underlying concrete type that's used to instantiate the type. So like in ba8, for instance, our number of values is not determined by ba, it's actually determined by int 8, okay? That will tell you that there is 256 values. Now, technically, this ba example here, when I had this, I'm not entirely being truthful here. This one actually is since this is a sum type of foo, bar, and baz, this ba int 8 is actually, I take that back. This might actually, if I do foo of 8, I don't think, yeah, it's going to be ba array still. Yeah, so in this case, this by date is going to be 256 values. But if we actually passed in a data, let's do foo type foo 8 int 8. Give me a second here. You'll see something here, something particularly interesting. So if we do this, you'll see that what's actually construction is not a bar 8, it's actually a bar int 8. All right, and this is because technically there is no relationship between right now this type alias almost and this guy right here, right? But the point is if you go and create foo int and bar int and baz int, okay, for data constructions, right? The number of values, well, let me say foo int 8, bar int 8, and baz int 8, because the number of integers is fairly large. The actual number of the cardinality of bar int 8 here is going to be represented as 3 times 256. Now I'm going to pause here for a moment and let you think about this. But the reasons why, if you think about it, it's because foo int 8 is providing 256 values. Bar int 8 is providing 256 values. Baz int 8 is providing 256 values. And since it's a sum type, and we'll dig into this a little bit more when we're really driving into it. Sum types are usually their cardinality is computed using addition. Okay, and we'll see this when we talk about differences between sum types and product types. This unary constructor has a special thing. The fact that it can take on the number of values that its underlying concrete type provides means that in many cases you can actually just use the underlying concrete type passed in to instantiate the type to represent that type. Okay. The way you do this in Haskell is by using what's called the new type keyword, right? So here, if we simply change this from type to new type, we will not get any errors from Haskell, but what we get for free is from a compiler's perspective, you've basically told the compiler that anywhere that they use ba8, just go ahead and represent ba8 as an 8-bit integer, and you've optimized in a way the representation for that particular type, which I think is pretty cool. All right. New type is a special way of defining type construction. Okay. Unlike just using a normal data constructor, new types are technically not algebraic in that they cannot be a product type or a sum type. And additionally, a new type cannot be a constant. It can, a data constructor. That means it cannot be defined using nullary constructors like we were defining bool and other stuff. Again, this is mainly related to the compilation advantages of using it, right? The fact that you're ultimately defining the layout for a particular type means that using that type, that new type, has zero zero overhead. There's no runtime overhead at all because the underlying concrete type is what is used to actually go and compile that particular type, which is great, right? If you're especially you're using integer types and numeric types, right? If you're using a product type or a sum type, on the other hand, the Haskell compiler may have to go and do some additional work, especially when you're talking about defining what effectively is a struct type or a record when you're talking about products, or in the cases of sums, you'd ultimately want it to represent in the assembly some notion of a tagged union, right? So this is why new types get and deserve their own kind of syntax for defining them. Okay, and the side effect of this is when the compiler generates the final code, you will never know if the new type existed because the new type itself was subsumed by the underlying concrete type that instantiates it. Okay. We could see this type of new type when we use our dogs example here, because we could simply just create this and we'll end up, creating a new type. And now we can leverage this in normal type signatures. So let's say that we have a function that that determines how many dogs you have, right? And we can leverage this even for a larger thing with pets. In that case, what you would do is you could simply just go ahead and define a function called, let's say, too_many, that takes in the number of dogs, or we call it too_many_dogs, that takes in the number of dogs and return the bool, and then you can go ahead and say define, obviously here with pattern matching, the dogs that you will have. And remember, when you are defining a argument that is actually of type of a unary constructor, you have to specify with the actual argument like this. So you take in the n, because and instead of being like n::: dogs or something like that, you would have to go in and specify, if you remember, that what we're doing is we're taking an n, and this is of type dogs, and then we're going to use n inside the body of the definition. In this case, we have greater, in my opinion, greater than 2 dogs. It's too many dogs, just because it's crazy. All right, some folks might say 10 dogs, but I think 2 dogs there are a bit of a handful anyway. So now you have this way of providing something, as being n that has too many dogs. Why is this kind of important, especially? Well, I'm going to go back to using an analogy from using, say, again, C++ or other modern languages that you're used to, and particularly languages that support this notion of aliasing a underlying, maybe lower level primitive type with a name. All right. A lot of these weaker type systems use this aliasing feature to ultimately make sure that when similar disjoint types, but that are semantically they're disjoint types, that whose underlying representation is the same, they don't go in and accidentally be used incorrectly when passing into functions. Okay, so in this case, by not providing, if we provided a simple int here, we'd be in big trouble, right? Because now, what does this mean, right? We can accidentally, if we had a pets application, you could pass in the number of cats here, and you're in big trouble, right? Because you're incorrectly analyzing. Although the number of cats and number of dogs are represented by integers, this might be the wrong rule to actually go in and invoke. So by providing these kinds of aliases, you are actually providing better semantics to the underlying program, and you can actually go and reason through it, right? This is one of the beauties of having kind of this type system. But there's an additional advantage here when you're using new types, mainly that this notion of defining stuff falls also into the realm of defining type class instances. So it might be the case that although you have a underlying type, okay, that will give you the number of runtime values, it may be the case that you are actually requiring a different set of behaviors when dealing with this particular type. Okay, so I'm going to show this brief an example in a minute. I'm just going to pause here by kind of illustrating what we've just done here so far. So in the case of too many dogs, if you accidentally pass in, say, an integer here, it's going to complain. Obviously, you can construct num dogs from a literal. But if you pass in dogs 8, you'll end up getting a thing because we're breaking apart the type to get the underlying value, and we're illustrating that. And if you pass in too many dogs, dogs 1, and then you're actually good. All right. So to go back to our dogs versus cats example and this notion of defining a type class instance, instead of defining this, all right, let's go ahead and say that we have, okay, let's see here. Let's comment this out the old-fashioned way. Comment region. Okay, and let's go ahead and instead define a type class called too many. Right. This is the reference here is in chapter 11 as well. In the Haskell book, because the Haskell book kind of gave this really nice definition of what too many is. So we're just going to kind of adopt it to our needs here. It's the same too many instances, okay? When you're creating a type class, remember we name it. We name it too many in this case. We pass in a type variable because we don't know what type it is. If you are actually defining too many to be dependent upon other type classes on A needs to satisfy them, remember you have to also provide those and use the equals arrow sign rather than the dash arrow sign to actually go and determine whether or not those checks are working. And now that we have this definition here, we can just go ahead and say we have this function that takes in a type A and returns a bool. All right. Now that we have this, we can actually go in and create too many dogs where, let's do too many ints first. Okay, so this is an example of a type class instance on ints for too many. Okay. And we can actually go and define now, too many, and take in an argument n and n greater than 42, right? And now we have this thing. Now, but if you pass this guy, say, too many, and then you pass in, any integer, you're actually okay. Sorry, you have to actually go and provide. It's going to blow up because it can't actually figure out what numeric you're actually dealing with. We can fix this in a minute, but uh, uh, in this case, we're going to have to do 8:int, and then now. Let's see something here. What did I do wrong? Unexpected type. Oh, sorry, not class. What am I doing? Instance. Now we have it. Okay. And now this will work. And obviously, if you have 8, you'll see also if you don't provide it, it doesn't know what type you're dealing with because it doesn't know that it's a numeric type. Now, for folks who were here before, recall that if you, instead of doing this here, if you end up doing, say, instance num a equals too many a, where n is greater than 42, I think that's the correct thing. Illegal. I think I might be messing this up. Hold on one second. I think I have to do this here. Num a arrow too many a. Let's see if that works. Okay, that works. So now we have our 8. Call an int. We have a false. If we do 8, it's going to recognize that there's no definition defined there. But if you specify, an instance car on this, it's going to complain, and you'll see that here in a minute. If we end up, using, for example, a different type there. All right. So I will move on this one. Let's see if there's a way. Oh, wait. Let me do this. Num a equals too many num a. And let's see if that works. Namely, expected a type only as constraint. Okay, so this one. Hold on, let me go back to our definition for type classes. I am having kind of a brain fart here. Let's put up something here. And software. Okay, and let's see here. Got it. So the way you do that is to fix that, you would have to go in and actually do, like, say, if we had a different data class, we can actually go ahead and do that. That's right. So we can't actually use numeric constraints on this particular thing, but if you end up defining it on the instance that are being passed in for types, that's right. If you do that on the instance that's being passed in for a different type, and you want to use it, you could certainly do that. let's move on here. It's a little bit of a tangent, but that's okay. That's the beauty of us going through this. Now, so the reason why, some of you may be wondering why this works, but this here without it doesn't. And as I said before, it's because the the Haskell compiler cannot determine what type of numeric value it's trying to construct, because the number of numeric values that implement the num type class is a lot, all right? And that's something that makes it difficult for it to construct the right thing. So if you read this here, it says that you may want to use a type annotation. And why is that? Well, the reason why is because there's a potential instance of the type class defined on integers. So this is why it's considered an ambiguous type variable for the type too many, because it could not find it. It only found that it only recognized that it has to be a numeric, that it is of type numeric. So what it's telling you is well, there are all these different, integer types that you could deal with. Go ahead and specify what type it is too as well. So the top level error is talking about the specific fact that we're dealing with an ambiguous type that it couldn't recognize. That's A0. The bottom one is the type checking recognized that the literal is actually a numeric type, but it can't constrain it. So it gives you some options on how to constrain it and suggests that you use a type annotation to constrain the type. So let's use something other than, say, int here, all right? Let's use, say, for example, 8:int32. You'll see, because we didn't define the type class instance on int32, it's going to go and say, oh, well, we can't find one. The execution, the function application is ignored, all right? So that's something to be aware of when you are dealing with these like type class instances. So, okay, so there's a question here. If I define some type bound a variable, can I define a new type based on that? Okay, so if I understood this question, so if you have a finite type that you've defined, like say a record type, I believe you could potentially use it. The only thing is the type checker and underlying compiler may not optimize it the way it would optimize like primitive types. So you'd have to do some benchmarking there. Another comment was made regarding the number of values that bot8 is going to be provided. So I'm kind of curious. 8. Oh, no. Yeah, T is I again. I. You see that is bot int 8 there. If it was bot int 8 here, you have int 8 plus int 8 plus int 8, which is 3 times 256, right? Yeah, it's plus because it's a sum type. So the comment is that it was related to the sum type calculation for the cardinality. You're not multiplying. It's not the Cartesian product. You're not multiplying it. You're adding 256 3 times because each one of those will generate 256 values. Are there other questions? Okay. So here's where this type class stuff really is going to drive it home. So we have this dogs thing that we provided, right? So we can actually go ahead and with new type, and this is something you can't do with another thing that we defined. If you use the data constructor, the type synonym, if you use the type synonym approach, which we did here with if we use bar8 like this, the type synonym approach won't allow you to do what I'm about to show you, and we could even try it out. Okay, so for example here, let's say that you have our dogs. We can define on our new type, okay, dogs, where, and then how do you define the function? Well, we defined it earlier. We just need to do 2 dogs n to extract the value, and we could just go ahead and just specify, greater than 2, and that we've now defined exactly what we had before. So if we provided too many, and then we do dogs 3, we'll see that it's true. But if we say too many dogs 2, we'll see that it's false. All right, but let's see that if we try to define instance too many on bar8, right? Where, and we have to say too many, and if we use bar n here, we can end up saying n is greater than 3. Let's see what happens if we do this. All right. What happens? Holy crap, we can actually use that. That is interesting. Is it because, let me change this. Here, let me comment this guy out because this might be causing some problems. Okay. That's interesting. They may have changed this from the time that this kind of read this. I kind of understood this. Hold on. Maybe I messed up the type synonym in Haskell. I thought that was correct. Oh, my apologies. I'm using new type, not. I'm using data, not type synonyms. Type synonyms are defined. I forgot. Type synonyms are defined with type. Okay. We have to make sure I keep track of that. Let's do this as say that. Now I should be okay. And let's do this like this. Okay, and that's what I expected it to do. Okay, so with type synonyms, which are, again, defined with the type keyword, we are dealing with essentially an actual, as the name stands for, an alias, an exact alias for an existing type, right? Because of this, Haskell says that it won't allow you to define a a specific instance declaration for this underlying type. The main reason for this is mainly because of the fact that, well, as you can read the comment there, T cannot be, it has to be one of many different types, or T cannot be a synonym. So, and the reason why this arises is mainly because of the fact that there might be cases where you want to use the underlying type representations implementation of the type class. And there's no real way of dispatching once you've provided your own custom implementation to go back and do extra work and then dispatch on that other higher level type. It doesn't do some sort of like method combination, I guess is what I'm trying to say. So as a result of this, if you want to do this kind of aliasing, right, and you want to have the things, and you can't, and you want to, more importantly, specify a type class instance on that alias, you're better off defining just a new type, which allows you to then use this as is. Okay. One thing to note is, and this is something particularly interesting, is up until now we've defined type instances as type class instances for many different type classes that we provided from our review of the chapters, but we've never been able to take one of these type classes that we've defined and actually have the compiler auto-generate implementations. Is that even possible? Well, if the underlying representation can be used, then we could certainly allow it to figure out to generate the specific implementation for a new type by simply allowing the compiler to recognize the fact that oh, wait a second, this is just a new type, which means I can use the underlying type class instance to actually go and implement the logic. The way we do this is by using, and this is the first time I've seen this, so this is going to be particularly interesting, is by something called so everyone has used pragmas before in other languages, I'm sure. Haskell has its own pragmas, but it has its pragmas with some additional features that will instruct the compiler to do stuff rather than oftentimes with pragmas in say something like C++, it's oftentimes used to define and enable and disable particular sections of classes. I'm sorry, not classes, sorry, of code, so that it compiles accordingly. Common use cases is for writing in the same code base code that's platform specific, where you have a pragma that defines whether or not you're using Windows or not, and then you go and enable or disable a particular piece of code by turning on that particular flag by using $D, and you just go ahead and now use that flag as is inside your code as if it was activated. The specific pragma that we're going to be introducing in this code is going to be something called generalized new type deriving, right? This is available as part of the prelude as far as I can tell, but it's not something that you can use as is when you're writing your own code and files. So, well, I take that back. It may not be available in the prelude. I haven't tried it to see if it's in the prelude. But if you're going to write language extensions, and this is one of those language extensions where it will take in essentially code that the standard didn't provide, a type class that the standard didn't provide, and then it allows to do some sort of generalization of and auto generation of that particular code. All right. So the way we define this is simply by just using at the top level. I don't think well, let's see if I could put it anywhere in the file and then see if it is. The examples had it kind of at the top level before the module was defined, but I think I could just simply do this. And the notation for it is you open curly brace dash, okay, hashtag, all right. Now we have what's called a pragma, right? And now we're using a language pragma, and language takes in a saying that we're using a language extension, and now we're specifying the actual extension here, right? And it looks like we can actually put it anywhere in the file, which is kind of cool. So you're localizing where we're actually using this. Now that you have this, okay, we've already seen how to define, without generalizing fragment. You've seen this right here with our dogs. Also, let me go ahead and put our dogs here in this location. And you've already seen that this is available for you, right? Let's do this too as well. Let's do this, then move this code around a little bit, right? Now, since we know that, actually, let's do this. We can also do this. Yeah. All right. What we're doing here without, if we know that we want to use the default implementation of the underlying type class instance. So what I mean by that is if the underlying type has an implementation of the type class and you want to just use that logic for your reasoning, you could just simply do what we're doing here is unwrap the knowledge from the actual type and then just dispatch on it. But instead of doing this, what would be even better is get this auto-generated for you. And now with that generalized new type deriving guy, you do get it. And if we just go ahead and do trivializing, sorry, not trivializing. If we just do too many here and we compile, you'll see it is not a stock derivable class. Interesting. Why did this work before? Okay, so it looks like I do have to put it at the top. Okay, so let me go ahead and do this at the top. And boom. All right. Earlier it looked like that because I wasn't using it, it didn't complain. It just ignored it. And now it started complaining. So now that we have this, if we call too many dogs and say 5, you'll see that it's calling actually behind the scenes the type class instance for int, and you'll also see that if we do info on too many, you'll see that it's a type class where we only define it on integer, and then we've also now defined the implementation because of the deriving for dogs. All right. Let's do some even interesting things. This given this too many types, we don't necessarily just need to work on single argument constructor type. We can actually write implementations on tuples for this too many types and have a type class for too many types. Let's try and see if we can adopt this to this exercise on handling a tuple like that's of type integer and string, shall we? One way of doing this is, let's say we use new type a pair equals, let's see, integer and string, and let's see if we could just simply do deriving eq show, and well, let's see what happens if I do this. What would happen? Compilation invalid syntax. Let's do new type. Ah, right. That's because it has to be a unary constructor, right? So so let's go ahead and do that and just simply instance too many, and let's call this on int in string where, and let's see if I could just simply do this x y x is greater than 42. Now let's see what happens. What is this complaining about? Illegal instances are distinct type variables. So let's see if I could do this. We might be having to use flexible instances as a language context. Flexible instances is in Haskell a language extension that allows you to essentially what was it? What was its purpose again? It was I gotta pull it up again because I closed off my tab for that when I was looking at it earlier. Let's see here, flexible instances. So flexible instances basically allow some rules to be relaxed from the type system to allow you to provide more more implementation details to an underlying type class instance, and allows such things like this to be possible. So as you can see here, if we now look at instances on too many, this guy will actually work. It will actually have an instance on the string, and all we do now is we've now kind of subsumed what we did with dogs. Although now we could provide anything. Like if we say too many 5 dogs, we will end up getting I messed that up. No instances, integer. Oh, my apologies. Hold on a second. Did I say int? Let's say integer. Here. Okay, let's try this. Now we get 5 dot, and if I do too many, if I say, 10 cats, it'll also say false. Okay, we can actually change this guy to playing tens, and it'll be the same kind of idea. Here, too many 11 birds. You see, oops. The only thing that's wrong there, as you can see, is if you mistype something, it's going to be thinking that it's some weirdness. But the fact that the ending lesson here is that with at least new type and maybe new type, it allows me to actually do this now. Let's see. New type a pair says integer string deriving eq show too many. Actually, we can't do too many. I don't know if this is going to work, but we'll see what happens. Illegal binding of the built-in syntax, right? Okay, that's why. And let's see if I do this, and then do pair, what happens? Okay, so it still will not allow me to do that with the new things. Oh well, all right. Let's move on. So we've looked at arities of different type constructions. We looked at some types actually quite a bit, and we kind of understand that we have to add the cardinalities of different data, right? We also looked into the length of this using enum from a bool to understand that, especially when you're dealing with particular types, you can actually use it to actually go and determine the number of valid types, especially for finite type sets, to actually help you reason the number of cases that need to be happening in the runtime things. Now, sometimes though you may want something that acts more like your normal structure, right? Here, that's where products come in, okay? Products, we've already seen this. This example here, this integer string is a type of product, okay? The number, of course, is going to be fairly large for this, but if you know, if you're doing int 8 by int 8 as a simple example, and you wanted to determine the number of values that are valid for int 8 by int 8, and we could say that this is an int 8 pair equals int 8 by int 8. This here, this type synonym, the number of values that represents in that product type is going to be a 256 by 256 or 256 squared. All right. The result of the cardinality for products, again, is based on multiplication. We can also, this specific type of product, actually, that you're seeing here with pairs, the book calls an anonymous product because of the fact that there aren't any labels associated with it. But the point is the product is like any other type. It will give you a way of, it'll give you a way of grouping different types of data into a single value, and then you can go and access different values through a specific accessor to know what they want. And especially for pattern matching, this becomes very, very useful. The cardinality stuff, I think it will take some time for you to recognize it when you play around with these sums and product stuff. So I'm just going to briefly end on our product set discussion with the fact that when you're handling products, it might be a good idea to go ahead and use, a type alias and a tuple constructor to actually go create your product, rather than, especially for anonymous products, rather than doing what the book was suggesting as an example, where you can also define a 2-argument constructor for per product, like here we go. Let's say we have data pair of bools equals pair of bools, bool. Okay, this is another type of product. Okay, the left-hand side, of course, is your type constructor. Your right-hand side is a data constructor, but it's a data constructor of 2 arguments. And you can see this if you do, I think, a pair of bools. If I did, let's say, data pair of bools, pair of given A to pair of aka if I do that and I do kind of pair of, you'll see that this is going to be a kind of function application. But you'll notice that this is still a product pair of bools because of the fact that we require both to be present in order for the construction to be a concrete member of this pair of bools. And we'll see this when we do pair of bools and we pass in, say, true, true. You'll see that this is returning pair of bools. But if we try to do pair of bools with just true, we'll get an error. Oh, we'll get a function. Okay, that's right. Okay, sorry. We'll take it. We'll get a partially applied function that would construct a pair of bools. That's interesting. Oh, that's right, because type constructors are also are effectively just functions of two arguments. So, so either notation is going to be particularly useful if you're doing anonymous stuff, okay? But sometimes you want to have named values associated with your product types, okay? Especially when you're coming from the struct or class world and you want to be able to access, specific values by name. You don't want to necessarily know or use pattern matching unnecessarily in specific situations. So at your disposal, another way of defining product types other than anonymous products and other than the way I just mentioned here in the case of creating our pair of bools example for product types. So right now, approach one is using the type synonyms on a anonymous product, i.e. a tuple. So we've already looked at this by doing type int 8 pair of int 8 int 8. That will give us 256 squared values. Type 2, we'll say using a 2-argument data constructor to define the product type. And we saw that with pair of bools when we do pair of bools, bool. These are all concrete types that I'm creating right now for the sake of example. Pair of bools. Oh, sorry. I'm not creating a type synonym. I'm creating a type. Okay, so now we have that. And then, of course, our third approach is using record syntax. So these are all the various ways of actually creating it. And here, we're just going to create, a standard. This is kind of typical definition that you want to use to define, kind of say, like a person. All right. So instead of using, a 2-argument data constructor, you can instead and kind of kind of justify this reasoning. Let me actually go and talk about justification on this particular thing. Okay. Let's say that we have person no record, right? And because I'd like to use person when we're doing record syntax later on. Okay, no record syntax. So forgive the name, but it kind of makes sense on here. And let's say that we have this make person that takes in a string that represents their name and an int that represents their age, and then string that represents their occupation. All right, deriving from, say, EQ show, all right? Because we want to be able to print this out. This here doesn't give you any sort of accessors, so we have to now define for this particular type accessors for specific things, all right? So let's say that we will have a function named name that takes in a person, no record syntax, and returns a string, okay? Now, to really go for this, you just basically can write the one case, which is I just want person, no record syntax, string, and nothing else here. And we could just specify, you know, sorry, not string. S, okay, and we'll just return the name, all right? Here, we have, what is the error? Not in, oh, sorry. Make person is what I need to provide here. Make person here, okay? And let's say this. Okay, that's right. We're ignoring these both. Now we actually have a syntax here. So if we go again, you know, create, say, a person with make person John Doe, who's 35 and is a janitor or something like that. Okay, and we now have a person here. If we ask for the name of a person, we now can get John Doe, right? But this is kind of tedious, right? We'd want to be able to just get some accessors already available for you, right? So instead of doing this, you could provide a better way, which is data person equals person, and provide the name of your fields, okay? So here we might have name and provide the type of it, say that it's a string, age, provide that's an int, and occupation. And we provide that has a string as well. And here we can also say we're deriving from EQ and show. And what automatically gets generated for you is now 3 functions, okay? If you look at name, age, and occupation. So if you look at the type of name, you'll see that'll take a person and string, type of occupation. You'll see also that it'll give you name string, and you know, obviously the age is going to take that person and give you an integer to represent the age. So now we could just go ahead and say a person now is just, you know, person, say Jane Doe, she's 27, and let's say that she is a lawyer or something like that, okay? So now if we type name a person, we'll get their name, age, a person, we'll see that they're 27, and if we do occupation of a person, we'll see that they're a lawyer. So you can see that this auto-generated thing from the file automatically is extremely useful, especially when you are dealing with you know, product types. So I started using quite a bit of this syntax just merely because this is, you know, I think pretty clean compared to, say, you know, trying to make your own tuple syntax and things. Finally, I think it's important to recognize that we have this. A final topic that we're going to be talking about is something that when dealing with algebraic data types, you have to recognize, and that is the notion of kind of like a normal form for Haskell's ADTs. But to begin with, we need to first understand that when we're talking about cardinality with products and sum types, all the algebraic laws that we are familiar with from arithmetic tend to be applicable here. This includes everything from, the distributive law uh, of addition, as well as what we saw earlier related to um, just product, Cartesian product being used to actually go and determine um, to to figure out the number of members of a product type. We can use the Cartesian product or just multiplication to define the number of values from each set to actually go and determine the number of values of the total type that we're dealing with. This also plays true with when you're doing like sum of products. If you're using a sum type that contains who has as one of its members, um, uh, say, actually not a sum type. If you have a product type who has one of its members is a sum type, then the total number of members or runtime values for it is going to be the multiplication of the product of the first value, the number times the the second value, and you'll know immediately how many members are going to be associated with this. Okay. The Haskell book kind of talked to this notion of this example by defining kind of some data types related to books, all right? And I think that's pretty useful to kind of go through. Let's kind of define this first, which is this is again in chapter 11, section 11.12 on normal form. If we have, say, some types, like say fiction, to determine one type of book, all right, and nonfiction. And the reason why you'd want to do this kind of like split is because there's this notion in Haskell that you can't use a type while permitting only one of its tablets as being one possible value. Remember, this is related to null-array constructors and pattern matching. We can't specify a specific use case for just true. So what you would have to do is you'd have to, it would be better to just provide these two different types, which will allow you to further categorize and further factor out some of the code that you would write later on. So we now have these two, actually we'll just do row here, driving show. And now we can just go ahead and say book type here will be either fiction book, fiction, right, or nonfiction book, nonfiction. Okay, deriving show, right? And you can use this for one of its things, and then you can also, let's say define, so example, defining books in their books, authors, and the book type. Okay. So we might end up having, say, like an author, which is like a type alias to, an author name is type alias to a string, and we can then define, like, say, an author being an author of, and then you have, say, sorry, not this, do this, of author name and book type. And then we have now a product type of this, all right? Now, when you have this kind of like structure here, okay, we have this data constructor that's considered that ultimately has, you know, a name, okay, which is a string, and a book type, which is a sum type. You want to know, if you want to know the number of values that are happening at runtime, you're going to have to go and compute the distributive property like we were discussing earlier, right? It'll be essentially the number of authors determined by the cardinality is going to equal the number of potential author names times the number of fiction books plus the number of non-fiction books. And you can see easily that you can apply the this is that, this, and that. And for folks not recalling the pipe syntax, but the pipe syntax is the number of elements in a set. This particular definition here, though, because it doesn't actually allow you to compute this, it makes it difficult to compute this because we haven't expanded it. It isn't in what's called normal form, okay? It can be evaluated to kind of break apart the different values that are available, but it's not actually in a way that makes it easier to actually compute the number of values. So it isn't a normal form based things. If we were to define, though, say fiction and nonfiction as based on, you know, if we put it based on the name instead, this is our non-normal form version. We can actually get a better definition that will allow us to easily indicate what the number of values that are happening at runtime, which will make it easier for us to reason about our programs. Recall in this notation right here, okay, that this is the number of authors, right? And recall again that the distributive property where it says that if you have a product times a sum, this is the same as author name times fiction book plus author name times nonfiction book, right? We could actually write and define our type definition exactly the same way, all right? So instead of defining it this way, you can actually go and say, you know, data, an author is a set of fiction author names and or non-fiction author names. And that what you have effectively done is sorry, not EQ. We don't want them. Yeah, get the EQ and show. So now we are actually getting close. We will actually be able to, you know, define our names, our fiction authors and our nonfiction authors, and we're good. The only difference is we have to parameterize, in effect, our fiction data types and our nonfiction data type, and everything just squares, falls in place. So we can go ahead and do that. Okay. Hold on. Did I mess something up here? Maybe I messed something up here. Author name, type string, author name, type string. Oh, yeah. Let's go ahead and comment this. And we're good. This, oh, sorry. Let's go ahead and put this guy here. Actually, you know what? We don't need this right now. Let's go ahead and put this back here. And go and put this here. Okay. So now all the types kind of match up. Okay, now I remember why this was a particularly interesting example to go through. The reason why that was all happening is because we're dealing with null array constructors, and we've effectively defined a unary constructor here that conflicted with our null array constructor that we provided earlier on. So the fix was to kind of get rid of some of that notion. Now that we have this is in normal form. Okay. The number of fiction authors is going to be based on the number of names. So it's author names times fiction, and author names times nonfiction, and we have the total number of authors. We're in normal form. Okay, no more further evaluation is required. You don't have to do anything crazy. The only time it's going to be necessary is when you do function application on the computation. We've seen these kinds of normal forms things all over the place in other papers, in other languages, actually. And actually, when you start talking about programming languages in general, you've dealt with one of the more famous or more well-known examples of a normal form-based sum type, and that is an expression type. If you're dealing with expression types, oftentimes you have expressions. Let's say if you're building, like, say, a arithmetic calculator, those expressions tend to be sum type or products distributed over sums. And there's other examples on how you might want to end up building some of this stuff. I encourage you to go and look at dealing with products over sums, an example on expressions on this. But the representation of the sum of products that we're seeing here, it happens in so many different places, and especially where if you're writing like fold expressions over representation of data types. Oftentimes you might end up doing this when you're dealing with like generic programs or generic algorithms or metaprogramming. A lot of those types end up becoming simpler to represent when you're using Haskell, especially if you're using this sum and product notation compared to composition, object composition in most other languages. One thing to note about generic algorithms that the book mentions that I am totally not convinced is that they should be necessarily used judiciously, just because as long as you have the appropriate type classes associated with the function, you are dealing with essentially a generic function with sort of type constraints on it. So I'm a little wondering why the authors of the book say that using representations of some product type, especially when you're writing functions or over the representations of these data types, especially when you're implementing generic algorithms or metaprogramming. It should be used judiciously. So I guess I would have to encounter enough Haskell code to recognize when and where a particular case is doing this. But I'm just going to end with the fact that when you're dealing with these normal form-based things and you're writing generic code that leverages them, just be careful as to potentially blowing up the number of runtime values you're going to have to test with. So analyze your types and see where, when, and where certain things are more appropriate and prune accordingly so that you don't have to write a lot of pattern matching rules. So I'm going to leave the next maybe 10 minutes for questions. And next week, we will talk about construction and deconstruction, value construction and deconstruction, more on the function types, more on kinds, and then we'll get into some examples like polymorphic lists and binary trees. So are there questions? Well, if there are no questions, I appreciate you all for joining me today. Next week, we'll finish off our completion of Chapter 11. Probably do some of the exercises too as well, just to check it out. In the live coding session, you'll see me butcher a lot of the Haskell since I'm kind of learning with you guys. If there are potential ideas and thoughts on how we're kind of covering this material, feel free to go ahead and provide them in the YouTube comments. And for those of you who are watching our live stream on YouTube Live, on YouTube, I suggest you subscribe to the Atlanta Functional Programming Meetup channel. And if you're interested in actually joining us in the discussion, both either on stream or after hours, after the talk is done, that is, feel free to join the meetup actually at meetup.com and give your feedback. Before I leave, just a quick announcement and a reminder. Atlanta Functional Programming's mission is to promote the functional programming paradigm as kind of a dominant paradigm. We are not specific to any programming language, although if you're wanting to do a compare and contrast of different programming language, programming paradigms, we're up for that discussion. We are not at all, being smug about just using FP. Although we would encourage more folks to look at the FP paradigm before trying to, dismiss it. Atlanta Functional Programming, to pursue that mission, is looking for speakers. If you have a specific topic in mind that you would like to discuss from a software engineering perspective or architecture perspective, and you've leveraged functional programming for a particular use case, anything from hobbies or projects or any products that you've built on the side, by all means, contact me on Bugram on both the Discord server and on the Functional Programming Slack channel. I'm usually just squatting there just to talk to people. I'll be more than happy to discuss and entertain ideas and talk ideas that you may want to give. So until next time, I'll see you guys next week. I hope you all have a